Precalculus students, welcome to your 6.3 notes. We're going to talk about vectors today. This is Mr. Hale, and I hope you'll follow me in this discussion. I think it's a good topic and one that has a lot of applications. So quantities such as force and velocity involve both a magnitude and a direction, and we can't characterize them by a single number. For this reason, we use directed line segments or vectors that can demonstrate both direction and magnitude. Now, some of you have taken physics, you've seen these before, you may have some background, but I think this explanation is pretty good. It's not just a magnitude, it's not just a direction, it's both. So we're kind of dealing with two things at once. And just some quick terminology on this first slide. Any of these vectors you see here would be equivalent because they are pointing the same direction and they are of the same length, therefore they're the same direction and magnitude. Okay, now again down here we have some notation. Now this will be new to most of you, but if we have a vector that starts with the point P and ends at point Q, it would be given by the difference between Q1 and P1 and the difference between Q2 and P2. Now we put it in this component form. Effectively, it's the same as saying we have an X value and a Y value. We've seen that before every time we've done an ordered pair on a graph. So this Q1 minus P1 is effectively like the X value, and the Q2 minus P2 is like our Y value. All right, so if you want to find the magnitude or the length of the vector, you might recognize this. It looks a whole lot like the distance formula. That's because, well, mainly because it is. It's the distance formula. Some of you may think of a Pythagorean theorem, same concept. All right, so that's what we're talking about with vectors. Now let's get into some practice. First, this says to find, and some of you may be looking at this and saying, what is that? But that means the magnitude of vector AB. So if I want to find the magnitude of vector AB, we would do this. We would just simply say it's the difference in our X values for the ordered pair. So we're going to have 3 plus 2 quantity squared. That's minus a negative. And then we'd have 2 plus 3. And again, that's coming from 2 minus negative 3 quantity squared. We're taking the square root of the whole thing. So this is essentially our change in X values. This is our change in Y values. And we'll get the square root of 50. And you could write that as square root of 50. Or if you want to pull out the 25, you can make this 5 times the square root of 2. I would say either of those answers would be just fine. For the magnitude, if it's said to approximate, you know how to use your calculators to do that. All right. Just a little more terminology, what we can do, some operations with vectors. We have two vectors here, u and v, where u is defined as u1 comma u2 and v is v1 v2. If we want to find the sum of the two vectors, we can just add them together like you see here. We can also do scalar multiplication of vectors. Both of those will come into play, so just keep those handy. All right, so let's look at number 2. It says to find the component form and magnitude of vector v that has the given initial and terminal points. So I'm going to start by doing the component form. I'm going to say that vector v would be the terminal minus the initial point. So that's going to be 6 plus 2 for the x value and negative 4 minus 2 for the y value. And again, what we're talking about here is taking terminal minus initial, terminal minus initial. This allows us to see what the vector's magnitude, and later on we'll talk about direction as well, but it would be 8 and negative 6. So in other words, it moves forward 8 spaces in the x direction and down 6. If I want to find the magnitude, I can just use that component vector I just found. We don't have to go back to the original. We can use this, and we'll have an 8 squared and a negative 6 squared, and I'm going to take the square root of that number. And if you know, actually this is a Pythagorean triple, 6, 8, and 10, or you can just do 64 plus 36 and take the square root, and you'd get there that way as well. All right, a little scalar multiplication and addition going on here. So on number 3, it says, first it says 2u. These are pretty quick. We're just going to do 2 times, and then we'll have a 3 and a -7. That'll give us the vector 6 and -14, so we can do scalar multiplication. You can add or subtract vectors like you see here. We have 2, 1, minus, and then vector u is 3, -7. So I'm just going to subtract the basically the x values, and 1 minus -7 would give me 8 for the y value. And I have to be a little careful about saying x and y values. We can think of them that way, but it's not an ordered pair. It's a vector, so don't take it too far down that pathway. All right, and then our last one is u plus 3v, and I'm going to guess you guys are able to do 3v in your head, so I'm going to take that vector v and I'm going to multiply everything by 3, and I'll get 9 and -4 for the result after I add those two vectors together. As we move forward to the next slide, you can see the box at the top, and I know on your copy it's kind of small, but we have lots of properties. If you're having trouble seeing them on your paper, just go look in your book. All these will be listed together in your textbook in this section 6.3 as well. I'm not going to read through all these properties, but you'll recognize some of them. It's like, you know, identities and distributive property and inverses, associative, commutative, things of that nature. And we've seen these before. All right, and so it's just showing you that they apply to vectors as well. Now, here's what we do need to talk about. Many times it's useful with applications to find what's called the unit vector. It's a vector that has the same direction as some vector v, but it has a unit or a length or a magnitude of exactly 1. It's kind of like the unit circle has a radius of 1, the unit vector has a magnitude of 1. And it's really a simple calculation. The unit vector is you take your vector v and divide it by the magnitude. So let's do that. Let's find the unit vector. We'll talk more about applications of this as we move forward later on, but the magnitude of vector v would be 5 squared plus 12 squared. Take the square root of that, and you may have noticed, like, hey, that's -5, Hale, and you only wrote 5. You'd be correct. We'd be squaring the whole term anyway, so it's really not going to matter. So our magnitude is 13. So my unit vector here, I'm going to go ahead and call it u, would be just simply -5 over 13 and 12 over 13. The nice thing about that vector is it focuses only on direction. It doesn't tell us anything about magnitude, but that can be useful when we get to other problems. All right, as we look to the next slide, everything we've looked at up to this point essentially has been about component form of vectors, but there is another form called linear combinations. We'll probably use component more than linear combinations, but this is still a really valuable way to do it, and some of you may actually like the linear combination method better, so you're always free to use linear combinations, and they can be nice. They can, you know, again, sometimes we like them better than component form if it's just personal preference more than anything else. You can see the example here. Basically what we do is put everything in terms of i's and j's. So essentially the x term of our vector would be the I term, and then the y term would become a j value. So 3i minus 2j is equivalent to the vector 3, -2. All right, so let's write the linear combination for the vector that's given to us on number 5. Well, I mean, we need to start probably by finding that component form just so we kind of know what we're looking at here. So we're going to do the terminal values minus the initial, so -1 minus 3 and 2 minus -6. So our initial vector, and this is in component form here, would be -4, 8. So if I want to write it as a linear combination, I just simply do -4i plus 8j. By the way, don't confuse that I with the imaginary unit. They are not connected to each other in any way, shape, or form. Sorry. Smart guys that write the fat books made that decision, and sometimes they make decisions that can be confusing later on. I hope that's not one of them. I think it's pretty obvious when you do it. All right. The thing I like about linear combinations, and I think you might too, is that in some ways it's a little more logical when we add things together because we're used to adding like terms and we get to do that a lot. So if I want to do 2v plus 3w, you can see w and v are given to us here. I'm going to go ahead and just write it like this. 2v would be 6i minus 4j. 3w would be negative 18i plus 15j. And so 2v plus 3w, I'm just going to combine like terms. Negative 12i, negative 4j plus 15j gives me plus 11j. There's the component form of 2v plus 3w. And I misspoke. Did you catch it? I said component form. It's obviously a linear combination. So let's begin our discussion of angles in terms of vectors as well. We've talked a lot about magnitude and the two different forms, component and linear combinations, but we haven't talked about angles, so we need to start doing that. So let's say we have the vector negative 6i plus 6j. Now if you think about it in terms of what that would look like on the grid, it would be something like this. There's your xy coordinate plane. If we go 6 left and 6 up, our graph would look something like that. There is our vector. Sorry, bad drawing, but you get the idea. Effectively, the deal is here, that point right there is negative 6 comma 6. All right, that's the key, is where that vector ends. The terminal point is negative 6, 6. Now, what we're looking for is this angle right here. That tells me the direction for this angle. Now, if you're thinking about this in terms of the unit circle, you may already recognize, like, hey, wait a minute, that's in the middle of quadrant 2. I know the middle of quadrant 2 is exactly 135 degrees. Okay, so sometimes you get values that you can just simply use prior knowledge like that. Okay, something that's horizontal or vertical, or something that goes to a middle of a quadrant, things like that, unit circle values. Now sometimes though, like on B, you get values that you may not necessarily recognize, and I would say probably won't recognize unless you're a lot smarter than I am, which is very possible for the record. But unless you, 7 and 4. So I'm going left 7 and down 4. That is not a very typical place that we would see on our unit circle. And sorry, I missed my mark there. But our point here is negative 7, negative 4. Now what's going on is we're going left 7 and down 4. So what we can do is actually use a little bit of trigonometry. I'm going to call this angle theta reference. Okay, so if I want to find theta reference, I can just simply use the tangent function. So I know the tangent of theta reference would be, well, it's 4 over 7. They're both negatives, but we'll be all right with that. And let's see, theta here would be about 29.74 degrees. Now here's the only thing, and that's theta reference, by the way. The only thing about this is we're not really looking for that angle. We're looking for the angle that starts and goes around like this, right? So effectively, I just need to add 180. So my real angle theta that I'm looking for, my directional angle, would be 209.74 degrees. So when we do these directional angles, we always want it to be from the positive side of the x-axis. All right, we're going to keep going. What you see here is connected to it connects the trig that we've been studying to these vectors. I'm not going to read through all this, but effectively all these terms like u equals the vector x comma y, x is cosine theta sine theta, and you can see it in its linear combination form as well. And you can see down below, this may even be more useful. If you want to write vector v and you know its magnitude and you know its directional angle, you can use this, I don't know if I want to call it a formula, but this format maybe, to find that information. Really, really useful right here. So we'll use that as we move forward. And when I say we'll use it as we move forward, I mean very quickly we'll use it as we move forward. How about number 4? We're given a magnitude and we're given a direction angle, right? So what I'm going to do is go ahead and find the component form of the vector by using the formula we just saw. I know that I'm going to have the magnitude as part of the situation, but it's also the cosine of our given angle and the magnitude times the sine of the given angle. And I think you guys know by now, sine of 45 and cosine of 45 are both square root of 2 over 2. So what do I end up with? Well, 2 square root of 2 and 2 square root of 2. So I just found the component form of the vector by knowing the magnitude and the direction. Those are the two things that we need to be able to answer that question. For part B on number 8, I'm actually going to show you two ways to approach this problem. One of them, we'll start with this. I'm going to use the unit vector method. So I'm going to call this vector right here vector W, just so we have a name for it. And I want to find the unit vector that will give me the direction for the vector V that I want to use. So the magnitude of W would be the square root of 2 squared plus 3 squared, which is square root of 13. Again, I'm just using distance formula or Pythagorean with those two values. And then what I'm going to do is find the unit vector for W. I'm going to call that U sub W. You can call it whatever you want, but that's the notation I'm going to use here. And I'm basically just going to do 2 over the square root of 13. So I'm taking the x value and dividing by the magnitude. And then I'm going to take the y value and divide by the magnitude as well. So that's my unit vector. Now, why do I need the unit vector? Because if I know the direction in terms of a unit vector, all I have to do is multiply by the magnitude, and I'll have my vector. So vector V would be 5 times the unit vector. And that would look like this. It would be 10 over the square root of 13 and negative 15 over the square root of 13. Okay, again, as you guys know in this class, we aren't picky about you rationalizing. If you'd like to, feel free. All right, I'm going to show you another method on this one because some of you may prefer something that's a little more, and this may be more intuitive to you perhaps, but 2i minus 3j. You could think about that vector W. It goes something like this, right? And we know if we drew this triangle, this would be like in a ratio of 2. I'm going to put an x there. I'm going to say that's 2x and that's 3x. And then we know the magnitude of this vector is 5. So again, I've used the direction from 2i minus 3j by using this ratio 2 to 3. And then I'm using the magnitude from v, which we know is 5. And then we can just use Pythagorean theorem. So we'll have 2x quantity squared plus 3x quantity squared equals 5 squared. And we end up with x being equal to 5 over the square root of 13. Now you may notice we run into a lot of the same numbers. Okay, so there it is. 5 over the square root of 13 is our x, but remember we have to go back in, and when I say x, that's like the number that we'd multiply by. So when I plug it back in, I'm going to be moving right 2 times this value. So 2 times that value would be 10 over square root of 13. And as I move down, I'd be multiplying by 3, and it's in the negative direction, so that would be negative 15 over the square root of 13. Honestly, you can choose your method. If you're comfortable using unit vectors, that may be preferred, but if you like this second method, that's fine too. And I know I did that quickly. You may need a bit more explanation. All right, find the component form for the sum. We got to do some addition here, folks, of u and v with the given directional angles. All right, so what I'm going to do is actually just find two separate vectors. The first one, I know the direction and I know the magnitude. So this is going to be 4 cosine 60 degrees and 4 times the sine of 60 degrees. So again, that cosine, we connect with our x value. The sine, we connect with the y value. You may have seen that before. Well, in the unit circle and everywhere else we've done trig, we've done that same thing. All right, and now I'm using the magnitude of 4 and the angle of 90 degrees and plugging that into the second vector. And I'm going to simplify both of these before I do addition. So the cosine of 60 is 1/2, so I'm going to have 2. The sine of 60 is square root of 3 over 2, so this is going to be 2 square root of 3. The cosine of 90 would be 0, where the sine of 90 would be 1. So if I want to do u plus v, I just have myself a basic addition problem, don't we? So my x value is 2, my y value is 4 plus 2 square root of 3. And we're to the final problem, number 10. Now, I know you guys can read this, but we have two forces with given angles and magnitudes. What I'm going to do is find, when it says to find the direction of magnitude of the resultant of these forces, essentially what we need to do is add them together. So I need to give these some names. I'm going to call this vector u. I'm going to call this one v. Okay, so that means this angle 45 goes with u and negative 60 goes with v. It's really very similar to the last question we did, where I just need to find two separate vectors. So we know vector u has a magnitude of 250, and an angle of 45 degrees. So it would look like this: 250 cosine 45 degrees and 250 times the sine 45 degrees. Where I know that vector v is set up the same way, but my force is 130 and my angle is negative 60 degrees. Now, if you remember odd versus even, you know we can ignore that. With the cosine of 60 or negative 60, they're the same thing. And for the sine, we can just change that and make it 130 times negative 130 times the sine of 60 degrees. All right, so I'm going to go ahead and clean these up a little bit. We're going to have 125 square root of 2 here, and we're going to have the same thing for the y value on vector u. On vector v, the cosine of 60 is 1/2, so this will be 65. The sine of 60 is square root of 3 over 2, so we'll have negative, and then half of the 130 is 65, so we'll have negative 65 square root of 2. That's my vector u and my vector v. Now what I want to do is I'm going to call this vector w as the sum of those two. We can just simply add them together. 125 square root of 2 plus 65. And 125 square root of 2 minus 65. And I wrote the wrong number there. That's square root of 3, not square root of 2. I think I said 3 and wrote 2. Minus 65 square root of 3. So there's my resultant vector right there, w. The only other thing left to do is we have to find both the magnitude and the direction. So to find the magnitude of vector w, we're going to use our distance formula. It may look a little ugly here, but we have these little machines called calculators that can do some of this work for us. You just have to make sure you type in the right numbers, of course. And then our other term would be 125 square root of 2 minus 65 square root of 3 squared. And when you do that work, you'll find that the magnitude is about 250.15 pounds. And the last job here is to find the direction of this vector. And we use the tangent function again to do that. And it's basically just our y value divided by our x value. Again, something we've seen many times. And I'm doing plus 65. And we'd get theta equal to, it looks like it's about 14.87 degrees once you punch those numbers in. All right, folks, I hope that lesson works for you. This could be a little bit of a challenging section for some of you, but you're all capable of doing well. We'll give you some time to work on it and to ask questions, to clean things up. You have a spectacular day.